Hello everyone, in this video we're going to be looking at section 8.2, which is integration by parts. Integration by parts is a technique of integration that can be applied to a wide variety of functions, but it's particularly useful for integrands involving products of algebraic and transcendental functions. So anytime we have the product of two functions in the integral, integration by parts might be a good method to use. Okay, so integration by parts is derived from the product rule for taking derivatives of products. So say I wanted to find the derivative of u times v, right? Two functions, u and v. Well, I would say, okay, leave the first one alone, derivative of the second, plus leave the second alone, derivative of the first, right? Another notation instead of the Leibniz notation is just putting primes, right? So I could rewrite this as uv prime plus vu prime, right? And I could write this as uv prime. Okay, so now let's integrate both sides. And we're going to integrate this with respect to x, because we took the derivative with respect to x. These are functions of x. So if I do that, I get on the left-hand side, when I integrate the derivative, I get just uv back, right? And that, well, actually, I can just write out that step. So I get this right, which gives me uv equals to the integral of u dv plus the integral of uv du, right? And now if I subtract v du to both sides, or from both sides, I get that the integral of u dv is equal to uv minus the integral of v du. And that is our formula for integration by parts. So if u and v are functions of x and have a continuous derivatives, then the integral of u dv is equal to uv minus v du underneath the integral, or inside the integral. So what this is saying is I look at this function that's inside the integrand, right? So this right here, and I need to figure out which function is u and which function is dv. And then I can find du, depending on what I chose for u, and I can find v based on what I chose for dv. Right? That's how integration by parts works. But the hardest issue with integration by parts is choosing which function is going to be your u and which one is going to be your dv in that formula. So we have some guidelines for how we should choose u and dv. First, we should try letting dv be the most complicated portion of the integrand that fits a basic integration rule. So in other words, make dv as complicated as possible so that you still know how to take its antiderivative, right? And then u is the other thing, the other factor, again, because these are products. The other thing is try letting u be the portion of the integrand whose derivative function is simpler than u. This is the guideline that I kind of think about more often. And the reason why you want u to be the portion that has the most basic derivative is because if you pick u to have a very basic derivative, then the integration by parts boils down to doing this integral, right? So we have too hard of an integral right here, so we do integration by parts and we make it into just this integral. Notice this integral has du in it, or in other words, the derivative of u. So if the derivative of u is really simple, then it makes that second integral really simple, which makes us able to solve it. Okay, so now let's go ahead and run through an example here. So integration by parts formula, I'll just write it at the top here so that we have it, is u dv is equal to uv minus the integral of v du. Okay, so in this example, our two, remember we use integration by parts for products. So the two things that are being multiplied in example 1 are x and e to the x, right? So in this case, x has a very simple derivative, right? The derivative of x is 1. So I should pick x to be u. So I say u is equal to x, and I need to find, for this formula, I need to find du. So the derivative of u is going to be, the derivative of x is 1, and then dx, right? Because we kind of chain on the derivative of that. Or if I did du over dx, then I would solve for dx and multiply by dx on both sides. So the dx always kind of hangs out at the end when we take the derivative of u. And now dv is the other thing, right? If x is u, then dv has to be e to the x. And again, we know how to take the derivative of e to the antiderivative of e to the x, right? That's just e to the x. And I should put dx here. So notice when I pick dv, I should get the dv should have the d to the x part, because when I integrated it, I need that dx. And once I take the derivative, the du should have the dx on it, because when I take the derivative, we gain the dx back. All right, that's just notation wise. Okay, so we've got our pieces of the puzzle. So the integral of x e to the x dx is equal to u times v. U is x, v is e to the x, minus the integral of v, which is e to the x, and then du, which is just dx. All right? So we get x e to the x minus, what's the antiderivative of e to the x? Well, that's e to the x plus c. Boom. And again, with all these examples, I haven't really talked about it too much, but you can always check your work, right? That's the cool thing about integrals, is once you find an answer that's the antiderivative, you can always take the derivative and see if you got what's inside the integrand. If you do, you know you did it right. Okay, so for this next example here, I need to choose my u and v, right? So here is an example where you kind of need to look at guideline 1, right? Guideline 1 says make dv the most complicated part, but that you can still integrate, right? Notice that I don't, off the top of my head, know the integral of ln of x, right? So this means that ln of x cannot be my dv, right? Because I don't know how to integrate that. So that means that u has to be ln of x, because I can take the derivative of the natural log, right? And so du over dx is 1 over x dx, right? And then dv is going to be whatever's left. So the other thing is x squared, right? And we know how to take the antiderivative of x squared, right? It's 1/3 x cubed. So now we run with our formula. The integral of x squared times ln of x dx is equal to u times v. So ln of x times v, which is 1/3 x cubed, minus the integral of v, which is 1/3 x cubed, times du, which is 1 over x dx. All right, so I get 1/3 x cubed ln of x minus the 1/3 can come out front. One of these x's will cancel out with the x on the bottom, so I'm left with x squared dx. I can integrate that, and I will get 1/3 x cubed ln of x minus 1/3 times 1/3 x cubed when I integrate that plus c. All right, so my final answer here is 1/3 x cubed ln of x minus 1/9 x cubed plus c. Okay, so let's look at another example here. This example is a little more complicated for two reasons. The first reason is it's a definite integral, so first we'll find the antiderivative and then we'll plug in our limits. The second reason is because it almost doesn't look like there's two things being multiplied, and at the beginning of this video I said the integration by parts is good for two things being multiplied. But really, I do have two things being multiplied, right? I have sine inverse of x and dx, right? So here, I need to let dv, well actually, let's let du Nope. Try that again. What's our formula? We need u, right? U is going to be sine inverse, right? Because we know how to integrate we know how to take the derivative of sine inverse, right? So the derivative of sine inverse, you may not know off the top of your head, but it's one you can look up pretty easily. And it is 1 over the square root of 1 minus x squared, right? And then I'm going to let dv be my other factor, which is dx, right? And the reason why another reason why I chose u to be sine inverse is because I know my two things are sine inverse and dx, right? And I need to choose. I can't let u equal dx, because how do you take the derivative of dx? That doesn't make sense, right? But I can take the integral of this, because if I took the integral of both sides here, the antiderivative, I'd end up with the fact that v equals 2 x. Because if I've 1 there, in other words, this dx is like a 1, if I take the antiderivative of that, I get x, right? So my formula here is sine inverse of x dx is equal to u times v, so sine inverse of x times x minus the integral of v du, so x times, and remember I should have written a dx there, x times 1 over the square root of 1 minus x squared dx. All right, so this looks like x sine inverse of x minus the integral of x over 1 minus x squared dx. Okay, so at first glance you're like, why did we bother doing integration by parts? We had some hard integral and we got another hard integral. However, this hard integral over here we didn't know how to solve. Here we do know how to solve it, right? This is going to require a u substitution with u equaling to 1 minus x squared, right? Which means du over dx equals minus 2x, which means that dx is du over minus 2x. So substituting that in, I get x over the square root of u times du over minus 2x. So that gives me minus 1/2 times the integral of u to the negative 1/2. All right, when I rewrite the square root of u, and now I take the antiderivative, so I bump up the power, so that becomes positive 1/2, but I'm dividing, so this becomes multiplying by 2, u to the positive 1/2 plus c. So I get minus the square root of what was u, 1 minus x squared plus c. Right? So my final antiderivative was the integral sine inverse of x dx was equal to x sine inverse of x minus, right? I've got two minus signs, so plus the square root of 1 minus x squared plus c. Okay, so now I need to actually solve the definite integral, right? So now we know the integral from 0 to 1 of sine inverse of x dx is equal to x sine inverse of x plus the square root of 1 minus x squared evaluated from 0 to 1. Right? So sine inverse at 1 is going to give me pi over 2, and be 1 times sine inverse of 1 is pi over 2, and then plus 1 minus the square root of 1 would be 0, and then I would get minus, so I guess I can fill in all these points for you here. So this would be 1 sine inverse of 1 plus the square root of 1 minus 1 squared minus 0 times sine inverse at 0 plus plus the square root of 1 minus 0 squared. Right, so here I get pi over 2 because that's sine inverse of 1. This is 0. This is 0, and this is 1. Right, so I get minus 1. So pi over 2 minus 1 is my final answer, which is approximately 0.571. All right, a couple more here. Okay, so in this problem now, again, we let u be the one that has the more simple antiderivative, and dv be the more complicated one that we still know how to take the antiderivative of. So here, sine x is more complicated than x squared, so we should let dv be sine x since we know how to take the antiderivative of that. So here we let u equal to x squared, which means du is equal to 2x dx. We let dv be equal to sine x, and v would equal to the antiderivative of sine, which is negative cosine of x. So we get x squared sine x dx is equal to uv. So x squared times negative cosine x minus v, which is negative cosine x, du, which is 2x sine x. So this is negative x squared cosine x plus 2, we can pull the 2 out front here, 2 cosine of x. Try that again. There's an x in there. So let's rewrite this as x cosine of x dx. I don't know why I put sine x there. It should be just dx. Okay, so now we're like, oh crud. Again, why did we do integration by parts when I still have this hard integral? Well, this integral now can be solved with integration by parts again, because it's multiplying two things together. Right? It's multiplying x times cosine of x. Anytime you have to do integration by parts twice, you have to be really careful about if you had a minus sign still there, but in this case it's not too bad because there's a plus sign. Okay, so one thing to be careful of, if you have to do integration by parts, you must be consistent about your choices in u and v. So for example here, now I could not choose u to be cosine and dv to be, if I try to do u equals cosine of x and dv to be equal to x, I cannot do that because that contradicts my choices that I chose at the beginning. So I have to choose u equals to x, which means that du equals to just 1 dx, and dv equals to cosine x, which means v equals to sine x. I have to be consistent. So now going back up to the beginning here, or going back up to the previous equality, I get negative x squared cosine x, and now plus 2 times this whole thing, right? Because this whole integral that I'm multiplying by 2 is the integration by parts. So it's uv, so x sine x minus v du, so minus sine x dx. All right, so I got minus x squared cosine x plus 2x sine x minus 2 times the integral of sine x dx. So minus x squared cosine x plus 2x sine x minus, now what's the antiderivative of sine? It's minus cosine, so this is plus 2 cosine x plus c. Which is the correct answer. Oftentimes when you see an x squared with a sine or cosine, or if you see x squared with an e to the x, you'll have to do integration by parts twice. All right, so that was the key to this problem. Okay, so secant cubed x dx. So in this one, you're thinking, okay, maybe this is like that, the one we had before with the sine inverse. So we should let secant cube be our first one, and dx be our second one, right? But that is not the case. What we should do here is we actually need to break up secant cubed into two different things, which is secant squared and secant, right? So let's break this up. First, we see that secant cubed x dx is equal to the integral of secant squared x times secant x dx, right? So now we got to figure out what to choose for u and v. Well, secant squared is the more complicated one, and we do know how to take the antiderivative of secant squared. The antiderivative of secant squared is just tangent, right? So it's more complicated. We know how to take its derivative, or I'm sorry, its antiderivative. So dv should be secant squared x, which means u should be secant x, right? So du over, not du over dx, du is equal to the derivative of secant x is secant x tangent x dx, and then v, the antiderivative of secant x, is tangent x. I think I've been leaving off my dx's here. Apologize. dx, dx. Got those ones. dx. Sorry. Okay, back to our problem. So the integral of secant cubed x dx is equal to uv. So secant x tangent x minus v du. So minus secant, or v du. So tangent x times secant x tangent x dx. So here I get secant x tangent x minus the integral of tangent squared x secant x dx. Now I can replace this tangent squared with secant squared minus 1. So in general, tangent squared x is secant squared x minus 1, right? That's a trig identity. So this becomes secant x tangent x minus secant squared x minus 1 secant x dx. So now let's distribute the integral sign and the secant x at the same time. So secant x tangent x minus, so I'm distributing the integral sign and the secant, so minus secant cubed x dx plus, because I have a minus sign there and a minus sign here, so plus secant, in this case just secant, the integral of secant x dx. Okay, so we're here. You're like, oh crap, well, how did we started out with secant cubed and we got a secant cubed, right? Notice we have a secant cubed here, and that was what we started out with. That's not necessarily a bad thing, right? Because notice this is an equation, right? So what I can do is add the integral of secant cubed x dx to both sides. And if I do that, then I get 2 times the integral of secant cubed x dx. And what am I left with on this side? Secant x tangent x plus the integral of secant x dx. Okay, so 2 times the integral of secant cubed x dx equals to secant x tangent x. Now we need to know the antiderivative of secant x. So off the top of your head, you may not recognize what this is, but it is the natural log of the absolute value of secant x plus tangent x. All right, that is what that integral of the antiderivative of secant x is. Okay, but we're not done yet. Last step. We want secant cubed x by itself because we want to figure out what secant cubed x is. So my last step here is divide everything by 2. All right, so the integral of secant cubed x dx is equal to 1/2 secant x tangent x plus 1/2 ln of the natural log of secant x plus tangent x, plus c. So in some of these problems, you may have to play this game where if you end up having, if you end up doing integration by parts and get an integral that's the exact same as your starting integral, then you may have to bring it to the other side and keep solving. Right? That's perfectly fine, and that'll actually happen quite a bit with some of these. Okay, so now let's talk about what's called the tabular method. It's not really easy to explain via just explanation, but it's easy to explain through an example. And these are going to be helpful in examples just like this one. So remember when I said if you have like an x squared with a sine or cosine or an e to the x, oftentimes you need to do integration by parts multiple times. In this case, you'll have to do it twice because you need to take the derivative of u, which will be x squared in this case, 2 times to get it to go down. Right? And you'll see what I mean when you work with these more. So here we need to do integration by parts twice. And we did an example of integration by parts twice, and it wasn't too bad, but you can see how it can get a little bit complicated, and it's possible to screw up some of your negative signs, right? So the tabular method is nice because it helps alleviate that. Okay, so here's what we do. We decide what our u and v is. Here in this case, this is just like the regular integration by parts. So I'm going to let u be x squared and let dv equal to sine of 4x, right? And now, instead of writing out the formula a bunch of times, we're going to create a table, right? And this table will have, this will say alternate sines. The second column will be u and its derivatives. And the third will be v prime, or let's say dv, because that's what we call it, dv and its derivatives. Okay, and essentially we're doing all that work that we would do in the integration by parts, but we're writing out in this nice table method, so that way we don't have to worry about the signs. So alternating the signs, we're going to start with the plus here. And what is u? U is x squared, and dv is sine of 4x. And now we go down. So we're going to alternate the signs. Now we get a minus sign. So the second column is u and its derivative. So I need to take the derivative of x squared, which is 2x. And now the third column says dv and its antiderivative. So I need to take the antiderivative of sine of 4x. So remember, if I take the derivative, I would chain on 4, right? But since it's the antiderivative, I chain on the opposite of 4, or 1/4, right? So this looks like 1/4. The antiderivative of sine is negative cosine of 4x, right? And now I alternate signs. Go plus. I take the I take the derivative of 2x here, which gives me 2. And now I take the antiderivative of this, the negative 1/4 hangs out for the ride, right? Because it's a constant. And now, once again, when I take the antiderivative, I get a 1/4 because I need to chain on the opposite of what the derivative would be. And then the antiderivative of cosine is sine of 4x. and then we do it again. So I do a negative sign, and then the derivative of 2 is 0. Here's how I know I'm going to stop. Right? This is my last line of the table. So we stop when the derivative is 0. So now I should have multiplied this all out. So this is 16, so negative 1/16 hangs out front. And then again, I need a 1/4 because of the 4 on the inside. And the derivative of sine is negative cosine. So I need this to be a positive cosine of 4x. And then we could go ahead with 16 times 4, that is 32. Or I'm sorry, 64. Right? Okay, and this one was 16. We can go ahead and multiply that. So this is negative 16, or negative 1/16, sorry. Right? Okay, and so now this is how this works. If I wanted to find this integration by parts, I would say, okay, I want to find the integral of x squared sine of 4x dx. And here's what I'm going to do. Here's the pattern. I go straight across, down 1. Straight across, down 1. Straight across, down 1. And those are what I'm going to be multiplying together. So here I should multiply x squared, a positive sign, with x squared and sine, or nope, I go down one more. So x squared and negative 1/4 cosine of 4x. And then now I have a minus sign, minus 2x times minus 1/16 sine of 4x, and then plus 2 times 1/64, 1/64 cosine of 4x, and then plus c. Right? Simplifying this, I get negative 1/4 x squared cosine of 4x minus, plus 1/8 x sine of 4x plus 1/32 cosine of 4x plus c. And this is my final answer here. So as you can see, that might be a little bit easier. It's a very nice step-by-step process for when you have to do the antiderivative twice. It just organizes your work a little bit so you don't have to worry about parentheses and staying organized, right? But if you did this the original integration by parts way that I showed you, you will get the exact same answer. Thank you.